Webb just photographed galaxies that shouldn't exist, barely after cosmic dawn. They look too big and too mature, far too soon. Here is the quick takeaway. The early universe was busier than our best models predicted. Think of light stretched like taffy by cosmic expansion. That stretch shifts newborn galaxies into infrared, where Webb sees. Astronomers call this redshift, and higher redshift means earlier times. Webb stares deep, collects faint photons, then builds clean spectra. Those spectra reveal distances, ages, and the elements inside stars. One record sits around 320 million years after the Big Bang. It looks surprisingly grown, with heavy elements and dust already present. Bottom line, Webb has redrawn the first chapter of cosmic history. Picture a night sky so faint, your eyes would miss everything. The edge we mean is not a wall, but time. It is the earliest starlight we can still catch today. That starlight left when the universe was a few hundred million. Light travels at a fixed speed, so distance equals look-back time. Space has stretched since then, changing colors as wavelengths grow longer. Blue turns red, and visible light slips into infrared bands. Webb was built exactly for that invisible glow from cosmic dawn. Its mirror gathers more light than Hubble, with colder optics. A tennis court sunshield keeps instruments chilled, blocking warm radiation. At Eltwo it sits stable, shaded, and quiet from Earth. NIRCam photographs the deep fields with razor sensitivity and resolution. NIRSpec splits the light, delivering barcoded lines for precise measurements. MIRI reaches even redder wavelengths, seeing dust and cooler molecules. Together, they pull whispers from galaxies that barely started shining. Why care about this edge at all, beyond poetic awe? These first systems set the rules for every galaxy that followed. Their masses, metals, and black holes shaped the later cosmic ecology. If they formed faster, later galaxies inherit different stars and structure. So the picture is simple. Edge means earliest reachable light, stretched into infrared. Now how do we know those galaxies are truly that far? Astronomers use redshift as the distance dial, tied to expansion. In plain terms, bigger redshift means older light in earlier times. There are two ways to estimate it, quick and careful. The quick way compares colors through several filters, finding a sharp dropout. Hydrogen blocks ultraviolet, creating a cliff called the Lyman break. When that cliff slides into infrared, the galaxy must be distant. The careful way uses a spectrograph to measure exact emission lines. NIRSpec reads features like hydrogen, oxygen, and the Balmer series. The line positions give a secure redshift with small uncertainty. Why it matters is simple, because early claims can fool us. Some bright candidates at extreme redshift were dusty, much closer imposters. Webb Spectra fixed that confusion, confirming a true record population. One example is a JADES source near redshift 13.2. That corresponds to roughly 320 million years after the Big Bang. Its spectrum showed the break clearly, and metal lines as well. Metals mean earlier stars lived, died, and enriched the gas already. That maturity so early is the head-scratcher that stunned observers. Rule of thumb: trust spectra when claims feel extraordinary or controversial. Net result: Webb turned rumors into measurements and shifted the cosmic timeline. Then came the real jolt: sheer numbers of bright early galaxies. Several deep fields showed more luminous objects than models expected. The definition here is simple. Luminous means forming stars rapidly, pouring ultraviolet into space. Why that matters ties directly to how halos grow and feed. Galaxies live in dark matter halos that collect gas from filaments. The gas cools, falls inward, and ignites star formation in bursts. Feedback from young stars and supernovae usually throttles that growth. Early on, feedback should be stronger because shallower halos lose gas. Models predicted fewer big systems before 500 million years. Webb keeps spotting them, sometimes an order of magnitude more. That suggests star formation was efficient, clumpy, and highly time variable. Short, intense bursts can beat average expectations for a population. Example in real terms: CERS fields reported unusually bright counts near redshift 10. Follow-up improved the counts, yet they stayed surprisingly high. JADES and GLASS saw similar hints across independent regions of sky. Independent fields matter, because cosmic variance can bias any one view. What to remember: the early universe appears brighter and busier than forecast. Another surprise sat in the centers: black holes already punching above weight. An active nucleus means a black hole feeding, lighting up its surroundings. That matters because seeds need time to grow by eating gas. If they appear massive so early, our seeding story changes. There are several growth paths that astronomers test with data. One route starts with stellar remnants, then grows near the Eddington rate. Another path forms a heavy seed by direct gas collapse. A third option briefly exceeds the Eddington limit, growing faster than steady. Webb can separate these paths by reading line widths and colors. Broad lines and hot dust hint at fast feeding near the limit. Narrow features and cooler dust suggest slower, steadier accretion histories. In galaxies near redshift 7 to 9, Webb found active centers. Some show black hole masses of millions to hundreds of millions. The hosts are compact, blue, and thick with newborn stars. That pairing implies shared fuel and a rapid growth environment. Tiny tests ask if the light is from stars or nuclei. Mid-infrared bumps and specific lines often betray the nucleus. Bottom line, massive black holes were not latecomers. They rose alongside the first notable galaxies. To push farther, astronomers borrow nature's telescope, gravitational lensing by clusters. Lensing is gravity-bending light, magnifying and stretching distant sources. That helps because tiny early galaxies become big enough to study. The method works best with well-mapped clusters and deep exposures. Webb's sharp imaging reveals arcs, counter-images, and fine substructure. Those patterns let modelers reconstruct the lens and the source. Behind able clusters, Webb uncovered multiple candidates beyond redshift 12. Some were confirmed with spectroscopy, anchored by clean emission features. Magnifications ranged from a few to tens, depending on geometry. One-sentence recap: lensing lets us study fainter galaxies than Webb alone. Stakes rise here because we can finally sample the typical population. Typical galaxies, not only the rare bright outliers, shape reionization. Mechanically, photons from early stars stripped electrons off intergalactic hydrogen. The timing of that transition depends on how many stars formed. Lensed surveys tighten those counts, shrinking uncertainty on that transition. Example numbers show reionization largely done by redshift 6 to 7. With Webb, we watch that curtain lifting in direct detail. Net result: lensing plus Webb maps structure growth at cosmic dawn. Color is pretty, but chemistry is the gold mine for origin stories. In astronomy, heavy elements are called metals, everything beyond helium. Metals build planets, dust, and cool gas that forms new stars. If a galaxy already has metals, earlier stars have lived and died. That matters because the first stars, population 3, made the first metals. They were likely massive, hot, and short-lived, leaving hints. Webb hunts those hints in specific spectral fingerprints and continua. A strong helium-2 line without metal lines would be striking. A very blue continuum with no dust would be another clue. So far, results show extremely low metallicity, but not zero. Several redshift 8 to 10 galaxies look primitive, yet enriched a little. We also see bomber breaks, signaling older stellar populations already present. Dust appears earlier than expected, glowing in mid-infrared with MIRI. That suggests rapid cycles of starbirth, death, and enrichment in place. Example values show metallicities a tenth of solar, even lower sometimes. Those numbers mean multiple stellar generations happened in record time, so the picture is this. Chemical maturity arrived fast, but not from pristine first stars alone. All of this forces theorists to tune the dials on formation recipes. The definition here is straightforward. A model is a code that simulates gravity, gas, and light. We care because predictions must match counts, sizes, and spectra together. Otherwise, we learn the physics knobs sit in the wrong positions. Several changes help the match without breaking established cosmology. Star formation may be burstier, in dense clumps with high efficiency. Feedback may be directional, letting some gas escape while some returns. Early halos may cool faster due to molecular hydrogen pathways. Dust may hide young stars, making true rates higher than colors suggest. Simulations that allow these behaviors reproduce the bright counts more often. They also grow black holes quicker when fuel funnels inward efficiently. Example in real terms, updated runs now hit redshift 10 luminosity functions. They also create compact galaxies like those seen in deep fields. Observers test these runs by stacking spectra and measuring sizes carefully. Overlay numbers, sizes of a kiloparsec, and surface brightness trends. One-sentence recap: tweaks in baryon physics beat new fundamental physics. We keep lambda CDM, but we sharpen how galaxies light up early. We opened with a shock: galaxies that look too grown too soon. The payoff is plain. Webb is revealing a louder, brighter cosmic dawn. We defined what edge means, earliest reachable light stretched by expansion. We saw how spectra lock distances, cleaning up early confusion decisively. We watched black holes and metals appear faster than we expected. We mapped faint galaxies with lensing, tightening the reionization history cleanly. And we tuned models, choosing better dials instead of new physics. So what happens next is easy to imagine: more deep spectra. Bigger mosaics and clever lensing will push the timeline even earlier. If that happens, expect stranger systems and sharper tests of theory. Want more like this? Subscribe for the next deep field. Net result: the first chapter is being rewritten line by line.